welcome to the next 2 hours. You might think, what are we going to do in next 2 hours? So generally this is done best when you are drunk, but we don't have beer yet. So up until now what you have seen is basically open problems which either has been open for a long time or it is there somewhere, so everybody knows it anyway, and we just try to compile it. But in next 2 hours, what we'll try to do is to generate open problems. Okay, so I'm going to, okay, and so this is why I'll call this phase discussion/open problems, and please be open about open problems. Okay, so I have tried to organize this in a simple things, and if you have any other idea to generate open problems, you are welcome to tell me how to generate open problems. Okay. Okay. So, and now you can ask why we are trying to do this, because I think lots of young people get motivated when they see something explicitly said, oh, this is an open problem, rather than. So that was the whole idea. But before that I just wanted to add to this problems list, which Bart was talking about and Mihail talked about. So there's something very beautiful which is in this regard, which is called cut covering lemma. Okay. So what is cut covering lemma? So you're given a directed graph, say D, subset S and subset T. So here's your directed graph, subset S and subset T. What I want, X subset of VD with the following property. For every S prime subset of T, T prime subset of T, there exists a min cut, say C S prime T prime, such that C S prime T prime is subset of X. Okay. Now, see, so a trivial bound could be 2 to the power mod S times 2 to the power mod T times, say, because if you delete one of these guys, you will get a min cut. So there was a very nice, so in the paper of Krach and Wallström I think from 2012 Fox, they show that actually you can come up with an X in randomized polynomial time. Okay, polynomial time, but this may not be exactly the object, but it is, what was it, polynomial? No, it was randomized polynomial time. And the size of X was bounded by mod S, mod T, and times, say, R, where R is min cut size between S and T. So this is what the size was. Okay? But this is a randomized algorithm. So my question is it possible to give a deterministic polynomial time algorithm where we are able to find X of size even quasi-polynomial? And my personal belief is, with lots of recent developments about this perfect matching is in quasi-NC and all this, maybe these kind of objects are just around to show such size bound in deterministic polynomial time. But so there's a difference, because I'm asking a polynomial time algorithm, but all I'm allowing you is to, okay, give me a larger size object. Okay. Actually, I do not know any non-trivial size upper bound in deterministic polynomial time over this. So anything non-trivial in deterministic polynomial time would be interesting and useful. Okay, so this was my one of those query kind of question which we were talking before, that there are so many queries. Can we cover all these answer to all these queries by a polynomial size object? And so in that setting, this is the key to most kernelization, most randomized kernelization algorithm like OCT, above guarantee vertex cover, multi-way cut, and all these kind of things. So, Okay, so now, as I promised to you, that now we'll have some sort of discussion and open problems. And these are not the open problems which you see in the like in the back of the paper or in the book, but they are still interesting question. And the interesting, let's define that subjectively, and you can add to this with your subjectivity what you find interesting. Okay, we'll make up a list of this, put it in archive for people. So I'm just adding something really very random from my head. Okay, so I have made one class here. I will tell you what I mean. Chordal graph. Why did I choose chordal graphs? I have no clue, but I just chose. Okay, I have just added tournament plus. Okay, and I will tell you what I'm trying to do here. Okay, and we'll just not about graphs like CG, computational social choice, ... Okay. So now, if you have a very difficult problem for which you do not have polynomial kernel, there are several ways of going about it. One we saw before this talk was like we can ask for Turing kernels. Other is that we could start restricting the graph classes where we are studying this problem, where the problem is still NP-hard. Or I will talk around 5 about we can also relax the notion of the kernel question itself, and I'll define the notion of lossy kernel, and then I'll start adding some questions there. But for now, let's just stick to this. Okay, so let me add, just for your curiosity, one question everywhere. First, does disjoint path has polykernel on chordal graphs? Right? There was a paper long time back which showed that on split graph there is a polynomial kernel, but does it have a polykernel on chordal graphs? I know that disjoint path does not have a polykernel on general graph, so I have restricted myself to chordal graph because it provides me lots of structure. Does it has? I can ask multi-way cut. I can ask multi-cut. Right? For example, you know that multi-cut on trees has a polynomial kernel, but does multi-cut on chordal graphs, edge version, vertex version, do they have polynomial kernel? I have no idea. So just to give you an idea, so please add your favorite problem to one of this list. And what I mean by tournament plus, okay? So I was reading the paper of, lately we have got lots of kernel on tournaments because on directed graph most problems becomes hard if you just talk about general diagrams. But on tournament they are still tractable and we try to get polynomial kernel. For example, Miha will talk about lots of problems or graph layout problems in one of his talks, Turing kernels. So what I mean by tournament plus, okay? So there are lots of ways people have tried to generalize tournaments. And the two ways people have generalized tournaments, one was that they realized, oh, between every pair of vertex, there's a path of length at most 1. Like either S2T or like if you have any pair of vertex AB. And people try to generalize by saying, okay, I have a diagram where every pair has paths of length at most 2. Unfortunately, this definition is not very interesting because one can show that any problem which is actually hard on general diagrams turns out to be hard on even this graph family. But there was a very nice definition by Seymour plus someone else, and they said, what is tournament? It's a tournament is basically those digraphs which independent set has size 1. And they defined the notion of alpha bounded digraphs. So what is alpha bounded digraph? It is basically a directed graphs where the maximum independent set is bounded by alpha. So if alpha equal to 1, it is basically tournaments or semi-complete digraph, whatever you want to call it. Okay? So this is one way of, right? So I can also ask here questions like if feedback arc set, feedback vertex set makes sense here, then why not directed multi-cut makes sense? It is actually FPT. If you know a little bit of tricks, you can show it is FPT. So the question is whether it does admit a polynomial kernel, just even on tournament. Okay? So if you do directed multi-cut, I can ask directed subset feedback vertex set or feedback arc set. Even these problems are FPT on tournaments, but very bad running time, but their FPT is, hence polynomial question makes complete sense to study on these classes of digraphs, right? Now another question for which there is a very non-trivial but quite interesting kernel on tournament is directed bisection. So what is directed bisection? You want to find them into equal parts, so the number of arcs in one direction is at most k. It's also called one-way partition. Okay, so this actually has a polykernel on tournaments, but I don't know whether it generalizes to this. I don't even know whether it is FPT or not on slightly general diagrams, so I have no clue. So I'm just giving you some representative of questions which people can ask, and you can start. So please feel free to add. Okay, I'll come to this. One question which actually it's very so I was talking about, let's planar F deletion, and I told you that it has a polykernel of size k to the power f and family. Okay, and we showed with Bart, I think, is that if we take a slightly constricted problem of say eta tree depth modulator, and for this we had uniform polynomial kernel. What I mean by this, it was a function of eta times I think k to the power 6. Okay, so what is the eta tree depth modulator? So you are given a set x, and what is left has tree depth at most eta. So one question which I think is quite interesting is that what about eta path width modulator question? Does it has uniform kernel? I do not know answer to this question, and most likely it should be positive answer rather than negative answer. This is my by solution size, parameterized by solution size.
I think it's a valid question.
Daniel, I have checked. At least for this, I have checked literature. I have thought for some time. So, and my personal belief is it has, because of certain structure theory which is known about these classes of families of graph. It is more like, it's more closer to tree depth than like tree width. So at least I find this question very interesting. Either way, I mean, if you show me reduction, at least it doesn't follow from modifying our gadgets at least trivially. So this is what I said. So this is discussion. So if you think some of this question doesn't make sense, please tell me. Okay, so I wrote some set of questions, and now please feel free to add to this list. So this is what I meant by we can generate questions, right? I mean, it's not that we are bound to only solve planar vertex solution to write an interesting paper. Okay, I can add more, but I will add. So, but I request others to add to this list if you can think of something. At least I'm making you think. Please come.
One of the presentations in the morning, well, not quite sure, well, maybe other problems.
Yeah, please.
Somebody talked about planar stuff and mentioned this 2K, you mentioned this 2K kernel and smaller kernels maybe for planar vertex cover. But of course there's also for planar graphs the opposite question, so to speak, the dual question. What about a kernel for independent set? And so at least I am not aware of any, so planar...
Just
maybe
one
I
second.
got some here.
Just 1 second, Yanni. So that it is easier for you to be recorded.
So you might know that there is a 4K kernel, so to speak, with an sort of standard parameter, natural parameter, for independent set on planar graphs. Basically run your favorite four-coloring algorithm and then you have it, so to speak. But I'm not aware of anything better, which is, for instance, avoiding four-color theorem or anything like that. So maybe you know, you can prove me wrong here, of course, but I don't know. So anything better than 4K might be interesting, because it might give some insights also on planar graphs that might be interesting beyond independent set. Okay, that's basically all I wanted to say here for this edition here. Or maybe some remarks, please. Sorry, I'm almost bad at this, sorry. Still have the chalk.
Yes.
Okay. So the hitting paths in a tree, you can greedily solve this problem by looking at the deepest top of a path. But if you start looking at so you have a tree and a number of paths in this tree, and you want to delete a number of vertices so that you take at least one vertex from every path. And in the unweighted case, you can greedily solve it. But as soon as you go to the weighted case, it is NP hard already for...
These paths are given as input?
Yes, it's input. It's already NP hard for weights 1 and 2. But instead of looking at a tree, you can, if you have a number of paths in a line graph, so you have a number of paths here, you can also efficiently solve this using dynamic programming. So if you consider how much your graph looks like a line graph as a parameter, I'm interested in is this in FPT? So for example, in this graph, if I would remove this edge, then I would have two disjoint line graphs and I could solve it efficiently on both. And I call this the linear forest distance. So my question is the weighted hitting path in a tree parameterized by linear forest distance, is this in FPT?
No, no. Please come.
Well, background is another. See, kernelization is based on our rhetoric that gets us the money is about pre-processing, which is hugely important in practical computing. And there are other computing strategies which are important in practical computing, and one of them is greedy. Like greedy subroutines are all over the place. So some people here will have heard this little discussion about an open area before, but maybe to some it's new. So this is really industrial strength. Greedy subroutines in practical computing is huge. And there's this fantastic paper from a few years ago by Hartung and Niedermeyer. And this is background to what I want to talk about, which hasn't invented a nice name for it. And I did get money for this too. So could other people. So the topic where we're headed is called turbo kernelization. So okay. It's important when you're writing grant proposals to have good rhetoric. This sounds good. Turbo kernelization. What could that be? So Hartung and Niedermeyer did this thing which needed a name. And we ended up calling it turbocharging greedy. All right, so a big problem in practical computing is to take a graph and find the minimum number of colors to properly color the vertices of the graph. Industrial strength, tons of applications. And that's what they were looking at, was the minimum graph coloring. Now, how do you, and people in practical computing, they really don't do what you do. They, by and large, do heuristics. A lot of the heuristics have greedy subroutines. And a lot of the industrial strength packages for minimum graph coloring are more or less like the following. They do phase one, order the vertices from, let's see, to, oh yeah, high degree to low. No, it's the other way around. Low to high, low to high. Now notice that this is non-deterministic. So I'd have to be a little more specific. What do I do when you break ties and stuff like that? So there are various variations on this, but basically the structure of these heuristics in phase two is that you go down the list, so you get this list, and you go down the list. Remember, this is a greedy subroutine. You go down the list, you're starting with low degree. So I've got a vertex of degree 1. Hey, at the beginning, nothing's colored, right? So you start using, what is it, high degree to low degree? I know it's high degree to low degree. Somebody remembers. High degree, oh, low degree. High degree to low degree. I had it right the first time. Oops. You'll see why this makes sense. So I start off with a vertex of high degree. And I've got to color it. So I color it. Well then, I come to the next vertex. If there's a color available, I use it. I mean, maybe it needs a new color, hopefully not. But if it needs a new color, I just use it. It's a greedy routine, right? And then when I get down here, by the time I get down here in the list, I'm doing low degree. I will have used some colors. I've got a low degree vertex, so there's only a few colors it can't be. So there's probably a color available. Which one should I use? Oh, I'll pick one. So notice that this is sort of non-deterministic, right? And so is this, because unless I get really picky about how I break ties, I'm basically non-deterministically ordering the vertices from high degree to low degree. And then I go down the list and use a color when I need to, and hopefully when I get towards the end of the list, I've used some colors, there's colors available, pick one. And then how did I do? How do you know how good this, and then what you do is at the end of one run, you will have used some number of colors. And what you can do is to do it again. Just order it differently. And then you repeat, and then you measure the performance of a greedy heuristic for graph coloring by running this algorithm on a bunch of standard examples, and you see how many colors you used on these benchmark instances for the graph coloring problem. Right? And there are industrial strength packages that do minimum graph coloring, and they're based on greedy or variations on this same thing. Okay, so Hartung and Niedermeyer said, well, now notice when we were down here at low degree, there's probably a color available, so pick one. Which one? I don't know, just pick one. It's non-deterministic. So they said, well, what if we could have picked a different one? So there's also a moment of regret. You're coming along and, luckily there's one available, luckily there's one available. Darn, I've got to use a new color. Moment of regret. And I'm going down a fixed list from phase one. So they said, well, what if we backed up, and here's the parameter, k steps. Is it possible we could have made different choices on this suffix of the list that took us to our moment of regret, and get further down the list without having to use a new color? So the parameter is how far you back up. So it's an operational parameter in the context of a heuristic algorithm based on greedy. And what they showed was that this k backup for the greedy graph coloring is FPT. So backing up k steps, and then could I do this? All right, so this is FPT and how far you back up. Then they implemented this FPT algorithm. So all they're doing is a little FPT tweak on a standard heuristic based on a greedy procedure, and they beat all the standard packages on the standard benchmarks. Bingo! We can get paid for that. So that's not very well explored, is turbocharging greedy. It's waiting for more attention because, well, this is just a huge success, is that they did turbo greedy for graph coloring. Again, MGC, call it MGC. Well, then, in kernelization, what do? I've got my graph, and I have a bunch of reduction rules over there. And I look in my graph, and I could apply rule number 1 here, or here, or here, and take k down by 1, maybe, or reduce k, make the graph shrink, and then what? Well, maybe I would. Why should I have used rule number 1? It was rule number 2. I could have used that here, here, or here, and that would have taken me somewhere else. Well, the standard analysis of kernelization is we exhaustively apply all those rules, and in the worst case, we end up somewhere with a bound on the kernel size. But notice that we're basically doing a non-deterministic procedure, which rule to apply and where in the graph. And the virtue of preprocessing in the industrial strength setting, which is what we get paid for. You want to write a grant proposal and get money? Pay attention to what actually makes sense in applications. What's happening in the industrial setting is that you're taking an NP-hard problem and you're shrinking the input to here, and now you pay exponential in the size of the kernel. Well, it matters if I can go a little bit further and get a smaller kernel, because then I pay exponentially, in a smaller kernel. It matters. So it makes sense to say, well, what if, since this was all kind of non-deterministic, which rule do we apply and where do we apply it? In the case of kernelization, can we get to here? And the moment of regret is, none of those rules apply and I'm stuck. This is my kernel. Can I back up k steps, that's the parameter, and possibly apply the rules differently and get a little smaller kernel? Now, depending on the cost of, if it's FPT and it's not too expensive, that might be preferable. It might be worth it. It's an operational parameter. There's nothing to lose, right? I can always choose k to be 0 and then I'm doing what I used to do. It's a no-lose situation. So it behooves us in studying kernelization to ask, when can we FPT turbocharge kernelization? Nothing's known. This is just a riff on Hartung and Niedermeyer in some sense. But there is one thing that's known, unfortunately. It's kind of funny. There's one theorem that's known. And it's known about our lab animal, vertex cover. What's known is vertex cover has all these rules that will get you to degree, maybe Lars will correct me. I think we can get to minimum degree 3, and I believe it's known that you can't turbocharge it. This is also a perverse theorem of Niedermeyer. He shouldn't have proved it. Like sometimes you shouldn't prove theorems because they're just, they put everybody off the track and mislead everyone. One would normally expect that most kernelization can be turbocharged. But in the case of vertex cover kernelization, it's possible to prove, or at least for crown rule, that for vertex cover, no matter how you apply the crown rule reductions, you always end up at the same unique place. So turbocharging is impossible, at least for crown rule. And not all of the rules for to get to a minimum degree are interpretable as crown rules, but I think you can mix them and you still get a confluence theorem that it doesn't matter and you can't turbocharge. That's a perverse result, because we would expect that in practice most kernelization can be FPT turbocharged. And it matters in practical applications because we care about the kernel being small, because that's when the exponential costs begin. And that's it.
So let me just add a kernel question here. So if I remember correctly, things like k path, even k subgraph isomorphism has Turing polykernel on unidisk graphs. Am I right? On unidisk graph. But as far as I remember, it is open. What happens, for example, on map graphs, for example?
You're writing it on not about graphs.
Yes, I wrote CG, computational geometry. Okay? Like these are defined, okay? So I remember one map graph. I don't know about what happens to these questions on disk graph, for example.
Can you explain how you will put a Turing kernel on unidisk graph for k-path?
Please read your paper, Federer.
Oh, yeah.
Yes.
Okay.
We put the things on grid.
I will read it again.
Yes. It's there. Yes, please. Help.
With a problem.
Yeah.
This graph, this case of graph isomorphism.
No, even k-path, I don't know. I mean, maybe it has a Turing kernel for all they take over some good regions. I have no idea. This was like, take.
So this is not my problem, but I think that it originated, I think it was proposed by Christian Kołusiewicz during Dagstuhl this year, I think. We were thinking about it quite a lot, Astrid much more than me, but got not very far. I'm not sure if anything happened afterwards with this. But I find it a very nice problem. So this is about hitting bicolored P3s. And I'll write here that I've heard about it from Christian Kołusiewicz, but I think it actually originates in some paper that was recently published by them. Yes, but I find this a problem that looks weird at the beginning, but actually it has very nice combinatorics, and I will try to convince you about it. So the idea is, and it's very nice that I have two different colors, that you've got a graph, and the edges of this graph come in two colors. Some of them are blue. Some of them are, that's yellow, I guess. I hope so. Maybe it's red. Is it red? Okay, let it be red. Good. And the bad thing that we would like to avoid is such a thing. It's a bicolored P3. Namely, you've got one edge that is blue, one edge that is red, and one edge that is missing. Yes? And you would like to get rid of all such situations by deleting edges. Yes? So the question, delete k edges to get rid of those bicolored induced P3s. Yes? So why this sort of seemingly weird problem is interesting is because you can think of this as a clique that is colored with three colors. Yes? The blue color, the red color, and the transparent color. Yes? Where transparent color means there is no edge. Yes? And then you are trying to recolor the graph by recoloring blue to transparent and red to transparent to avoid free color triangles. Right? And interestingly, there is an old theorem of, I think, Erdos, as usual, from the 60s or 70s, that exactly characterizes clicks that are colored with, say, free colors, so that there is no free color triangle. And this you can get by taking, essentially, as far as I remember, by taking one vertex, yes, and repeatedly making the following operation. If you have already got a graph of this kind, what you can do, you can take a vertex and replace it with a graph that is colored with two colors, yes, which is like a proper blow-up. Namely that, say, if you have got a vertex outside that was initially connected by, say, a blue edge, then this vertex will be connected by only blue edges here. Yes? So you can replace a vertex by a two-colored subgraph here. Yes? And every graph that, every click that is colored with three colors and doesn't have a multicolor triangle can be obtained in this way. Yes? So you've got a nice structure theorem for the classes of outputs. Yes? And now you have a recoloring operation, yes, where here I can delete edges. That means recolor blue or red with transparent. Yes? So this is the formulation of this problem in this language. You can also ask about other variants of this problem. Yes? So if you have already this formulation, you can think about recolor at most k edges so that there is no free colored triangle. Yeah? So in this second variant, you've got a click colored with three colors. Yes? Your basic edit operation is recolor edge to a different color, and you would like to get rid of all the free color triangles. Yes? For both these problems, it is open whether there is a polynomial kernel. There are some easy reduction rules that you can do, but you will not, we weren't able to go far with them. And there is a hope that there will be actually a polynomial kernel because we have a very nice structure theorem for the classes of outputs. So I find this a nice problem to look at.
So let me this time definitely tell you something not about graphs. Okay, so.
But there are graphs there, not graphs.
Yeah, but he doesn't want those graphs. No, he doesn't want graphs. But unfortunately, there will be a graph. So, this is called orthogonal terrain. Okay? And because these angles either 90 degree or 270, okay? So this is orthogonal terrain. Yeah. And our objective is, so there are lots of people study this guarding question. So what is a guarding question? So you want to place guards on this terrain so that they're able to see either every point or either the perimeter or every surface. Now, I do not know the parameterized complexity of these questions when you are allowed to put guards anywhere, but it is FPT when your objective is to place guard. So again, parameterized by number of guards. and to place guards to see all this, what is it called? Let's call this vertices, to see all vertices. And I do not know whether it admits polynomial kernel.
Second, but what will be a kernel in this situation for this problem?
That's a very good question. Maybe you have to return me some. So look, this is a sequence of points, right? And so maybe you'll give me another different set sequence of points where if you solve things on this set of, like guarding these nodes, or you can think of this is basically a dominating set in visibility graph, right? So you're basically trying to get a kernel for dominating set in visibility graph, which I did not want to use. So basically you have given a graph on n vertex corresponding to this, which is visibility graph, and this FPT means you are making a dominating set, you are solving dominating set on this visibility graph. So now you have a very concrete question, right? But actually in FPT, we had to do some tweaking for these things also, like, okay, I mean, if you have such kind of terrain, then I can replace this terrain with something. So you can also do these kind of things.
And I also want to comment that if you get a polynomial kernel for this, then it implies that it is solvable in
Exponential time, yes.
time, which in itself is an interesting question.
Yes. Yeah.
FPT is exponential time.
FPT is exponential time. Yes. This is also in your paper. So
Tell me to read that paper also, right?
look, I don't do geometry that much, so some more points, lines. We'll get there.
I can comment something.
Please, not me.
Okay, so I just have a small comment. So in the first part of the open problems, Saket mentioned 3 heating set, and whether it has a kernel that has k to the 2 minus epsilon many elements. Now, I just want to say that the same question is also valid for 3-set packing. Okay, so for 3-set packing, okay packing, so you are given some universe U, so you are given some collection of sets, each one of them of size 3, and you are given a parameter k. And you ask yourself if you can find k sets in F that are pairwise disjoint. So here we have the similar situation. We know that we can get a kernel with k to the power of 3 sets. We can get k to the power of 2 elements. But can we do better in terms of the number of elements? And then you can ask similar questions for special cases. Like, for example, you want to pack induced P3s. Okay, so you have a graph, and you want to find k vertex disjoint induced P3s. Or you want to pack triangles in a tournament. So I will talk about it in Thursday, I think. We got for this particular problems kernels of size 2 minus epsilon. for example, for packing induced P3s, but can you get linear? Okay, can you get a linear number of vertices? So, I guess what I'm trying to say is that you can ask similar questions for 3-set K packing and special cases of it, like you can ask for 3-heating set. And of course also for D-heating set and D-set K packing.
I have something related to this. So maybe this is a small problem. So P3 packing, not induced, okay, just P3 packing. Now we have a kernel of 5K. Basically, this kind of maximum problem is easy to get a linear kernel, right? So the first question is, can you make it 3K? So you think this way. You want to find a K, P vertex disjoint P3, right? Now if 3K means now you have exactly 3K vertices. Basically that becomes P3 packing problem, right? So if you have such a kernel, basically they're equivalent somehow like that, right? The second question is, now the P3 packing problem has an approximation of 4.03 by second. So far, all the kernelization for this P3 packing problem also implies a approximation. Not necessarily, maybe, but so far, all the algorithm has that property. So in other words, this algorithm implies a 5/3 approximation, okay? So if you produce any kernel smaller than 4K, also having this property, that means you have a better approximation, right? So, of course, if you make this kernel without that property, that's great. And if you make a kernel smaller than 4K with that property, that's again great.
Are there any APX hardening bounds showing that you cannot go much below forward?
Sorry?
Are there any APX hardness lower bounds that showing that you cannot go much below 4?
I think it's APX hard, but the low bound is very, very small.
Okay.
But it's not going to be p-type.
Anyone? Yes.
So you can think of it as a question about polynomial time sparsification. You can also think about it as structural parameterization when the parameter is the number of vertices in the graph. And then clearly, if you have n vertices, your graph has at most n square edges, so you can encode your input in n squared bits. But the question is, when can you encode in n to the 2 minus epsilon bits, like n root n bits or something like that? And over the last years, together, especially with Astrid also, we showed that for a bunch of problems, it is impossible to get like subquadratic sparsification. And problems where we've been able to prove that are mainly problems whose solutions are determined by vertices. Like for vertex cover, you can prove such a lower bound. And in fact, Dell and Velmelkovic were the first to do it. And also for things like dominating set and for 3-coloring, you can do it. But one problem that currently we don't understand, and which is, I think, the simplest of this flavor, is the max cut problem. So you're given a graph, and you want to partition it into 2 vertex sets that maximizes the number of edges that cross in between. And now the question is,
is there a polynomial time reduction that reduces a max-cut instance on n vertices to some instance of a problem that's equivalent but has an encoding in n to the 2 minus epsilon bits? So in my talk on Wednesday, you'll see lots of different constraint satisfaction problems coming by, and there we know a bit about what you can and cannot specify, but those problems that we understand are of the form, I have a bunch of constraints, can you satisfy all of them? And you can think of maxcut as one of the simplest settings of a valued CSP, where you get paid a bit for every constraint that you satisfy. A constraint would be these two vertices end up on different sides, they get different values, and then the question is, what is the maximum value you can get out of an assignment? So this is, say, one of the simplest valued constraint satisfaction problems for which currently we don't know whether you can sparsify it efficiently, yes or no.
So I had a question, is that does it make sense to talk about cycle packing beyond H-minor free graph for kernelization? Say graph of bounded expansion, does it even make sense?
Cycle.
Did you just subdivide edges?
Okay.
So what's about bounded degree graphs?
It has polykernel. Then you can ask topological minor free graph, right? Makes sense, no? Anything else make sense?
What kind of graph?
Topological minor free graph.
And the closet with the fixed support for mine.
So I had a question here which I wanted to mention, but this is more like FPT, non-FPT. So suppose you're given a tournament, input is a tournament, and a, say, subset S, and you're looking for a cycle passing through S. Okay, so what is the question? Does there exist directed cycle passing through S? And there is an XP algorithm parameterized by S. Like, I think you can give, but I don't know whether it is FPT or not, or W1 hard.
All of us.
All of us. So like length could be like, it's like just T cycle in general graph, right? So on tournament you can get an XP algorithm for T cycle, but
In a tournament.
in tournaments, just tournament. But I don't know whether it's FPT or W1 hard. So it could be an interesting combinatorial question to try.
It's probably the same question as just this vertex disjoint paths in tournaments. So vertex disjoint paths in tournaments also have the same status. There is an XP algorithm, and it is not known whether it's
FPT or not. Okay. So okay, so my whole objective was in last 1 hour is to tell you that you can come with lots of interesting problems. Okay, so if you think of something, please send me an email with your problem, and we will include it in the list. But now I want to talk a little bit about lossy kernel, and let's see what kind of questions we get there. Okay. Daniel, would you like to define lossy kernel and start off?
You want me to talk?
Yeah, I'm tired.
We also have tutorial on lossy kernel on Thursday.
Yes, but it does not have open problem, because the guy who was supposed to give open problem didn't show up. He didn't get a visa. Seriously, he didn't get visa. They said you are.
UK to Europe?
Yes.
I mean, if you don't have to go to passport.
All right, so a very quick introduction to lossy kernels and the questions you can ask about it. I'm going to be purposefully hand-wavy about the definitions for several reasons. One is that if you go into the details of the definitions, it gets a little bit painful. And the second is that once you start thinking about these things, what the definitions should be becomes obvious anyway. If you start thinking about the open problems, the specifics of the definitions won't really matter too much. So, normal kernelization, what is it about? I give you some instance of your favorite problem. It has a parameter k, and in polynomial time, we want to produce something small, right? So an I prime with a k prime, and Mike would like k prime to be at most k. We are happy with k prime being at most poly k. So let's say now that k prime is upper bounded by something. Of course, this doesn't have to be poly. This would just be the size of the kernel. And the size of the instance is also bounded by some function of the parameter. And normally, what is it you would like to do, right? You would like to say that the two instances are equivalent. That's what we always do in kernels. But why is it that we say that the two instances are equivalent? It's just so that if we solved this instance, it would help us solve that instance. That's really the only reason we're saying that I prime k prime is yes, if and only if I comma k is yes, right? So usually we say, well, yes, if and only if yes, but really what we care about is that an answer here is useful here. All right, but now we ask ourselves, well, what if what we care about isn't just like, yep, or no, but here is a vertex cover. Here is a set of people who guard all of this terrain, or whatever. Like, what if the output over here wasn't just a yes/no answer? Well, then you better have to, and the answer here shouldn't be a yes/no answer. Then you should be able to translate solutions going backwards, right? And you better do it in polynomial time, right? Because if kernels are about polynomial time preprocessing, then you better be able to return solutions in polynomial time as well. Okay, and then you can define your favorite way of saying that if your solution, well, of course, notice that I could just solve this instance, right? I mean, I could run an algorithm directly on this instance and get something. So what you need for this thing that goes back is that a sufficiently good solution for this instance, you should be able to use it in polynomial time to produce something that is substantially better than what you can produce in polynomial time just staring at this instance, right? So you need to quantify that in some way or other. And one way of saying that is that optimal solutions should go to optimal solutions over here. So if I give you an optimal solution in polynomial time, you should be able to crunch it up with the polynomial solution to your original instance. And now you're going to be like, why is this guy talking about it? This is what we do in our proofs of kernels all the time anyway. Like every time we prove that our kernel is correct, then really what we're proving is that if I give you an optimal solution over here, I can translate that into an optimal solution over here. That's really what we've been doing all the time anyway. Now it turns out that most of the time when we're proving kernels, we can actually prove something stronger, maybe at like a little bit more effort. And this is that instead of optimal, we can say that, well, for any constant c, so for any constant c, a c approximate solution to the reduced instance, actually I can translate it into a c approximate solution to the instance over here. And you can go back and you can check that, like, say, the crown kernel for vertex cover actually has this property. The bus kernel for vertex cover doesn't have it, but if you work a little bit, then you can make it have that property, and so on. And basically, every time you make a kernel, almost every time you can make it have this nice property instead. Okay, it's a nice property, but we're still demanding more from our kernels than we have been so far. What if we made our life a little bit easier and said that, well, if I give you a C approximate solution over here, then I should give you a 1 plus epsilon times C approximate solution over here. So what if an optimal solution to the reduced instance only gives you a 1.0001 approximation to the original one? Now suddenly, these things do no longer have to be kernels in the traditional sense. For all practical purposes, they're almost as useful, right? If you're willing to pre-process and save a lot on the size of your instance, then if someone comes back with an optimal or near optimal solution here, you get a near optimal solution over here, that's great. You're only losing a tiny bit. And it turns out that the moment you relax your definition of a kernel like this, then suddenly there's lots of problems that used to not have polynomial kernels that do get polynomial kernels. Or in general, there is hope that you can get better 1 plus epsilon approximate kernels for all of your favorite problems than you can do for general ones. So on Thursday, I'm going to show you 1 plus epsilon approximate kernel for connected vertex cover and for partial vertex cover. So one problem that's FPT and doesn't have a polykernel, and one problem that is even W hard. Okay? So now you can ask yourself, well, which problems have kernels like this, right? And then you can, and when does it make sense to ask this question? It's if you don't know whether there is a normal kernel, right? Or can you get a kernel like this that's better than the best known kernel you have in this realm? So for example, you take all of your favorite open problems. For example, does directed feedback vertex set have a 1 plus epsilon approximate kernel of polynomial size? Hey, why not? Why 1 plus epsilon? I can even relax it even more. Can you give me a 1000 approximate kernel for directed feedback vertex set in polynomial time? So what do I mean by this? I mean, I give you a directed graph G, integer k. In polynomial time, you should do the following. Either say no, this graph does not have a feedback vertex set of size at most k, or you should output a new directed graph of size at most poly k. Right? So if someone produces an optimum solution to the reduced thing, you give me 1000 approximation to the original instance. Now, a word of warning, directed feedback vertex set is, I guess, known not to have a constant factor approximation unit games or p not equal to np? One of the two, right? Like, it's believed very strongly not to have a constant factor approximation. So if it now has 1,000 approximate kernel, you are doing better than the best one can do if you just see the instance, right? You would actually have to use your solution on the way back in a smart way. So you would actually be doing something non-trivial, hopefully leading the way towards actually a polynomial kernel for directed feedback vertex set. Okay, now you can ask, well, why stop at directed feedback vertex set, right? Why not ask planarization, right? Or this is deleting vertices to get a planar graph, right? It's not known to have a polynomial kernel. An easier question, can you get a 1,000 approximate kernel of, can you get a 1,000 approximate kernel of polynomial size? Well, here, poly k approximation is also open, so you have to play around with what is the ratio you're willing to go to, keeping it interesting. The same thing goes with multicut. Okay, let's do multicut. So multicut is known to have a 2 to the k cubed algorithm, known not to have a polynomial kernel. And let's see. It's known not to have any constant factor approximation algorithm under some reasonable assumptions. Okay, so let's do multicut. Okay, so does it have a 1 plus epsilon approximate kernel of polynomial size? What about 1,000 approximate kernel of polynomial size? Okay, so if I remember correctly, multicut, the best approximation algorithm for it is square root log k, right? So the best approximation algorithm is square root log k, right? Using SDP. Now, can you get me a polynomial size kernel for multicut, which is log k to the power 1/2 minus epsilon approximate? Right? Can you do anything better than the approximation algorithm? I don't know. This could be an easy. This could be an easy question. It could be as hard as improving the approximation algorithm. Who knows? All right. I have a ton of other questions I can ask, but if other people have other lossy kernels questions, I'm going to let you go first.
What is known about the FPT approximation of multicut?
What is known? See, multicut is FPT, right?
Yeah, but if I want to have a better running time, right, like 2 to the k running time, what would be the best approximation?
I don't think people have care. I mean, okay, so Marx and Rosgon did have an algorithm for multicut before the FPT algorithm for multicut. Does anyone remember what the running time for this is? But this is like before all of the cool stuff happened. So I mean that doesn't really yeah. So notice of course that a factor 1,000 approximate kernel for multicut would immediately imply a k to the k factor 1,000 approximation algorithm, right?
So k to the k factor 2 approximation is not hard, I think, because you can just partition the terminals and run a multi-vector. Sorry.
No, but that is like.
Oh, sorry. This is by parameterized by terminals. So this is not by solutions.
Okay. Yeah. So I mean, I don't think that this is. I mean, I don't think 1,000 approximation in k to the k time is something that people have spent a lot of energy on. So I don't think. I don't think it would be crazy to expect something like that to happen. Okay, so just to give you a little bit of flavor of these lossy kernel kind of arguments. So Bart here is asking, does maxcut parameterized by the number of vertices have a kernel with n to the 2 minus epsilon bits? Okay. Now, if you are willing to go for a 1 plus epsilon approximate kernel, then you can actually do order n, like 1 over epsilon square n bits. And all you need to do is you take your graph, and you take about 1 over epsilon. So you for every edge, you either keep it or you don't keep it independently at random with a small probability, so that the expected number of edges is about 1 over epsilon squared n, I think, roughly. Apply Chernoff bounds, magic. Every solution stays within like a 1 plus epsilon factor of its previous quality. So in particular, I like this question particularly much because if you were to show that you don't have a kernel with less than n square bits, then you really have to distinguish between kernels that are approximation preserving and kernels that aren't. Yeah. Okay, so I'm going to let other people take the floor, and if it gets too silent, I can come with more problems. Yep.
Yes, exactly. So together with some people in Prague, including Maso here, we looked at exactly this question of, well, it was more general about parameterized approximation, but we also talked about approximate kernels, and we looked at Steiner tree. Now the question I want to pose is about directed Steiner tree. Okay, so directed Steiner tree. What's the problem? So you're given a graph and a bunch of terminals, right? But one terminal is special. So yeah, it's a directed graph, right? One terminal is special. It's called the root. Okay, and now, yeah, for all the other terminals, you want to find a well, a tree in this graph here, such that for every terminal there is a path from the terminal to the root, right? So the solution looks maybe something like this. And you can, of course, use vertices in your solution that are not terminals. Yeah. Okay, and so I wanted to draw these tables here. So there are two variants of this. First is edge weighted, so means you have a weight function from edges to reals, and you want to minimize the cost of the tree. Okay, and so for the weighted version, the following happens. So okay, so the usual parameter, we've seen this before, right, is the number of terminals. So I'll denote the parameter in my table by k, but there are two parameters that I want to mention. So the first one is the number of terminals. I call the terminal set R. Okay, and now what happens? So in terms of algorithms, first of all, okay, the problem is FPT, and okay, you can use Dreyfus and Wagner, but there is another algorithm that's actually faster. For weighted algorithms, you can go to 2 plus epsilon to the k, and then some polynomial where the degree somehow depends on epsilon. Okay, like this. Okay, and then what about kernels? Polykernel. Well, for this parameter, I mean, just like the undirected case, there's no exact kernel. But okay, my first open problem is whether there exists an approximate kernel here. So for the undirected case, there is an approximation scheme here, so you can get this 1 plus epsilon. Okay, this question I haven't really thought about much, but it might be easy to answer. I don't know.
Are these silent determinants? Or? Yeah, R, so exactly, should I write this? Terminals, I denoted by R because T is the tree, so R is the terminal set. Yeah. Okay, that's the first question. Is there some approximate polynomial size kernel? Now there's another parameter that's interesting, which is the number of Steiner vertices in the optimum solution. Okay, so it's like if you take an optimum solution, let's call it T star, and you remove the terminals, so the size of this set. So in the weighted case, what happens is that this becomes terribly hard. So what we showed was that there is no, I mean, this is not too hard to show, but there is no f of k approximation, or rather, finding such a thing is W1 hard for any computable function f. Okay, so essentially you can't approximate this thing reasonably. And okay, that of course then also means that in terms of kernels, there is no f of k approximate polynomial sized kernel. Okay, but the other thing I wanted to talk about is the unweighted case. So that means like, yeah, you can think of it as every edge has unit weight, right? So unweighted, okay. So we also looked at that, and again, I'm going to consider these two parameters. Let's call it k, and I have the number of terminals, one parameter, and the other one is the number of Steiner vertices in the optimum solution. Okay, in terms of algorithms, now, yeah, this is of course still FPT here. You can do it a bit faster because now you can use subset convolution, so you get 2 to the k n to the O of 1 algorithm. And what about kernels? Yeah. So in this case, yeah, okay, it's the same as before. There is no exact, and if you think that this is maybe too hard, then you can also think about approximate version of this. So not entirely sure what happens here either. But okay, so now what we considered in our paper was actually mostly this case, the number of Steiner vertices. And here, so this problem is W2 hard. So this is not too hard to show. That was known before. But you can get a parameterized approximation scheme, right? So you can compute a 1 plus epsilon approximation in time 2 to the k square over epsilon times polynomial. Okay, so in contrast to the weighted case where you can't do anything like this, you can get arbitrarily close to the optimum. But okay, and now what happens for kernels is that we can show that there is no 2 minus epsilon approximate kernel for any epsilon. And sort of my main question that I would really be interested to know the answer for is, can you somehow match this? So could you get a 2 approximate kernel here? This would be really interesting. Or maybe this, I mean, maybe our proof is just not tight, right? I mean, or not good enough. Maybe you can show much larger lower bounds. Okay. Was there a question? Or?
Yes, so your objective function is the number of arcs in the solution.
Yes, yes.
But your parameter is the number of vertices that are non-terminals.
Correct.
In the solution.
Yes, that's right. Yeah. Also wanted to mention one more thing, which is actually which is not about kernels, but just proving lower bounds in this regime, like runtime lower bounds. Okay, so here you see this k squared. So in particular, like, is this optimal? Maybe there's a 2 to the k over epsilon algorithm. But even, I mean, proving some sort of, let's say, under ETH or something, a lower bound that somehow says you cannot do better than, say, 2 to the little o of k over epsilon times like poly n or something, right? This would also be very interesting. I have no idea how to do that. Questions? Okay.
All right. Thanks. More problems? I'll just hold on to this. So I guess I have a remark. I'm pretty sure this one, the answer is no constant factor approximate kernel for any constant. But it could be that you can do better than the best approximation. I guess we can talk offline on that. All right, so let me reiterate. I mean, hopefully you're starting to get an idea of how to generate lossy kernels questions. And this is, so generating a lossy kernels question, you do the following. You look at your favorite problem, and it should be a parameterized problem. Okay, so you look at your favorite parameterized problem, and you ask yourself, okay, what is the best polynomial time approximation algorithm for this problem when you forget about the parameter? Okay, so the ratio is going to be something, log n or something like that. Okay, great. Then you should always aim for kernels with a better ratio than that. Okay, because in the picture that I drew here, right, you can always, I mean, if you're trying to get a constant factor approximate thing here, yes, or something approximate thing here, then I could just run a polynomial time approximation algorithm on this instance instead of using something on the way back, right? So you should always aim for something that is better than the best approximation algorithm. So another thing is, whatever the kernel is, I thought I knew an exception, but it turns out we were wrong. Whenever there is a kernel, okay. So far, okay, it's like do we know an exception to the rule that, like, whenever we have a kernel of size poly k that goes from here to here, then that same kernel with tiny modifications gives you, perhaps not with the same constant, but the same exponent of the poly, gives you a one approximate kernel. Do we have an example? I don't think we have an example of this. So basically, you should always shoot for a lossy kernel, or 1 plus epsilon, or like approximate kernel that is smaller than the smallest known kernel for that problem. And of course, if you know that the so if you know that it doesn't have a kernel of some size, it's more valuable to get the 1 plus epsilon approximate kernel of that size. But if the problem is important enough in kernel world, like DFVS, right, and people aren't able to get, so then it's enough to get a lossy kernel of a size that people don't know whether it exists or not, right? That's also fine, because it gives you new understanding. But as you see in this table, there is a relationship between lossy kernels and FPT approximations, right? Because if you have a 10 approximate kernel of size 5k, if you brute force the thing over here, you get an optimum solution in time 10 to the 5k or whatnot, and you come back with whatever the approximation blow-up was here, and you get that approximation ratio for your original instance. So if you have a 10 approximate lossy kernel, you also have a factor 10 FPT approximation with the same parameter, right? So you should always aim for something that has better ratio than the best polynomial time and FPT approximation for that problem. Better ratio than, you should have better ratio than the best polynomial time approximation, not better ratio than the best FPT approximation. That's the trick, yes? And smaller size than the best kernel. Okay, so let's generate some questions, right? So, for example,
you have mentioned directed feedback vertex, planar vertex deletion, and multi-cut.
Yes.
Tree, right? So, multi-way cut is the vertex multi-way cut problem.
Yes.
Eric mentioned previously that whether deterministic polynomial kernel is deterministic classical polynomial kernel is still open, where the size is independent of the number of terminals, right?
Yes.
Now it has a 2 approximation algorithm, right?
Yes.
Now what about 1 plus epsilon approximate kernel of polynomial size?
Fantastic question. What about the 1.99 approximate kernel of polynomial size? Right. Yes, excellent. See, you've learned how to generate lossy kernels questions. Okay. What about let's do something that might be simpler. So we, and by we I mean me, Sakyat, Pilipchuk, Sigan, probably, yes? We showed that if you look at cut width, and you parameterize it by vertex cover. So if you remember, so what's the cut width problem? I want to order my vertices from left to right so that at any point in at any point of the permutation, if I cut the prefix from the suffix, the number of edges going from the prefix to the suffix, that is at most the cut width. So maximum. So the width of the cut width of a permutation is the maximum number of edges from a prefix to a suffix, and the cut width of a graph is the minimum over all permutations. So you can compute cut width in time 2 to the power vertex cover, something like this, of the graph, but we know that there is no polykernel. Okay, it is FPT. Yes, so in particular it is 1 plus epsilon FPT approximate for every epsilon. So the question is, so 1 plus epsilon approximate kernel is up for grabs, right? So 1 plus epsilon approximate kernel parameterized by vertex cover. For here we actually know that there is no polykernel. For example, if I remember correctly, for bandwidth parameterized by vertex cover, I think it's actually open whether this. So this is a nice question independent of lossy kernels. I thought I didn't have a non-lossy kernel question, but here is a new. It's not. I think it's Serge Gasper's question actually. It's an old but new to this workshop kernel question, and this is bandwidth parameterized by vertex cover. So bandwidth is I want to find the permutation of the vertex set and minimizing the longest stretch of an edge. Yeah? So a stretch is just the position of one endpoint minus the position of the other one. Again, relatively easy to see that it's FPT when you parameterize by vertex cover, but does it have a polykernel? We don't know. If you can't give me a polynomial kernel, give me a 1 plus epsilon approximate polynomial kernel. Yeah?
Then you can also ask imbalance, distortion.
Yeah, you can, yes. You can pick your favorite graph layout problem, search on Google. Is it known to have polynomial kernel parameterized by vertex cover? Probably the answer is no.
Go with 3 depths.
Yes, of course.
neighborhood error?
Absolutely. Your favorite parameter. Yes. Okay. Let's see. Someone who wants to interject at this point?
Yes, Daniel.
Yeah?
Why don't we ask, does, say, planar F deletion has uniform lossy kernel?
Okay. So this is, look, oh yeah, okay. So what is Socket pointing out here? Okay, so let F be a finite list of graphs, okay, and F deletion, then input is a graph G integer K, and the question is, does there exist a subset S of the vertex set such that the size is at most K, such that G minus S is F free. And F free means that it doesn't contain any graph in F as a minor. Okay? And now, usually, so this is, so I blame myself, or it's myself and co-authors, for making incredibly confusing problem names. We've called this connected planar F deletion, yes, where what is connected is not the solution, and what is there's nothing that's there's something that is connected and something that is planar, but it's not what you think would be connected and planar.
What is F is F.
Yes, what is F, okay? But so connected and planar refers to something in F, and so connected F deletion means that all H in F are connected, and planar F deletion means that at least one H in F is planar. So we even got the quantifiers wrong. Well, we got the quantifiers right, but we're inconsistent about them. And we should, but yeah. My excuse is that I don't think there is a single good naming convention for this problem. This is why everyone has their own name for it. But anyway, so okay, we're dealing with F deletion. You may or may not want to consider a situation where all of the graphs in the family are connected, because it makes the problem nicer. And you may or may not want to consider the problem where at least one of the graphs in F are planar. And what we know is that for at least planar F deletion, there is a kernel of size K to the sum function of the family F. And we know that this function has to be there. This is what we showed with Bart. But now the question is, if you do a 1 plus epsilon approximate kernel, can you then get, for example, some function of the family times K to the some function of 1 over epsilon?
Or even just F.
Or even the epsilon, put it down here. Yes? So the moment you go to approximate kernels, do you still need to have the dependence on the family in the exponent? The question about planarization, does planarization have a, so deleting vertices to get a planar graph, does that have a constant factor 1 plus epsilon approximate kernel? Of course, is a precursor to asking whether F deletion has some factor approximate kernel without the planar. If you're happy, you should include connected. Connected makes life a lot easier, and usually it's just like some technical stuff to put it in there once you have it, or to remove it. Yeah. Okay, so questions to this?
I have a remark about that. So the lower bound about these non-uniform polynomial kernels. I think it even holds if you parameterize by the vertex cover size. So I think for tree with add deletion parameterized by vertex cover, we already had the fact that it's non-uniform polynomial. So if you want to make the question at the bottom left easier and still interesting, I think you can parameterize by vertex cover.
Yeah, so I think I seem to remember that made the problem too easy. So I seem to remember that basically like, okay, so this is a good exercise, right? And to see if I remember correctly. And this is basically that like, if you parameterize like any eta deletion by any other eta prime deletion, you get 1 plus epsilon kernel sort of trivially. And it might even be that like any f deletion parameterized by any eta deletion has a 1 plus epsilon kernel sort of trivially as well. But it might not be. It might be not so trivially. It might be completely wrong. It's worth looking into. But yeah, it could be that the answer is sort of more boring than what one would hope for. Yeah. Right. So should we generate some more problems, or are you guys? It's 6:40 or it's 5:45. So okay. All right. Okay.
Let's thank all the people for generating questions and problems.